Oh, that actually is where I'm going to pick up, is the public key encryption demo. So let me plug this thing in, and we'll see a demo. Anybody have questions before we get started? It's looking pretty light for attendance out there. It's a what? Recitation day? For what? Oh. Oh, resignate. I thought you said recitation. I'm like, oh, everybody's going to recitations today? Oh, I guess they all want to learn stuff. Yeah, resignation day, yeah. We usually don't get too many resignations in this class, though. Like, at most 10%. Yikes. Hopefully we don't see a big uptick then. Homework 3 did hit pretty hard this semester, so we might see extra. We might see more. Is it graded? By tonight. So my deadline for the TAs is 1 week after the deadline. And then, so if grades aren't posted tomorrow morning, at the very least, you'll know I'm mad at my TAs, and I'm in the Slack channel yelling at them. But tomorrow morning, by then, you should see grades. Yep. How to use WebSockets to send 403 requests in Objective 4. So you don't have to use WebSockets. So WebSockets are a little bit tricky in Objective 4 for authentication. If you do want to use WebSockets for Objective 4, instead of doing the 101, you would send the 403. You wouldn't do the handshake. Your handshake is the only chance to authenticate, because the handshake is the only chance you have to read the cookies. That's the only time you're using HTTP during that WebSocket, during the whole WebSocket everything. So once you authenticate a WebSocket connection, that connection is authenticated for its entire lifetime. As long as that WebSocket connection, that TCP connection is open, it is authenticated, because you don't have another chance to authenticate unless you implement your own protocol where you're going to ping every once in a while and say, like, what's your username and password, or can you send me your token, which would be painful and probably insecure, especially if you're asking for the token, and a bad UX if you're asking for their password. So you authenticate, and instead of the 101, send the 403. And then don't allow, just don't establish the connection, so they can never send you a WebSocket frame unless they're authenticated. And then instead of generating a random username, you would actually use their username, of course, at that point, if they are authenticated. If you work at an HTTPS certificate company, like Let's Encrypt, can you do self-signed? Yeah, I guess. Like, for example, Google self-signs their certs. Like, they're their own CA. So yeah, the CAs self-sign their own certs. Which I would feel a little better. I mean, Google's not going to do anything silly, but I'd feel a little better if they got another CA to sign their certs. But I assume they have a lot of certs. They want to save some money. Certs, you can get certs for small traffic sites for free from Let's Encrypt. But once you have a lot more traffic, they do cost quite a bit. So do we not need to do Objective 4 if we use WebSockets? What? No. Seems like we can skip this part. No, you do what I just said. Who will watch the watchers, exactly. And that's one of my points in this lecture is all of security has to start with some base assumption somewhere. At some level, we have to trust someone. It's just the way it is. We have no way around that. So the root certificate authorities, we do unfortunately just have to trust. Can we skip Objective 5 if you feel like? You can skip any objective if you feel like it. You just don't get points for it. Yeah, exactly. You can resign the class and you don't have to do Objective 4 or 5 or any of them, or the project or reports. You don't have to do anything. Nobody's forcing you to do anything. Nobody's even forcing you to be in college. Like, I don't know if y'all realize that. Nobody's forcing you to do anything. All right, but let's see this demo. Oh, I don't even have the repo open. What the hell am I doing? So this is a really quick demo. Go into my encryption, and what I'm going to do is generate a key pair. I'm using JavaScript libraries, or JavaScript. My goodness, it's been too long since I did Java. I'm using Java libraries. I've been using too much JavaScript. I'm going to use RSA for my encryption algorithm. I'm going to generate my key pair which is going to give me a public-private key pair. I'm going to get my private key from it, get my public key from it. I'm going to encrypt the same text, the text I used in the example in the slides. I'm going to generate this, encrypt the same text twice, print the ciphertext to the screen, and then print the decryption of those twice, and then encrypt and decrypt. This is just using the libraries. It's Java, so there's a bit of bloat in the code, but this is just encrypting. I got to get an instance of the cipher, initialize it with the key, and then encrypt, and then base 64 encode. Other languages, that would just be .encrypt, but you know, who am I to say what's right or wrong there? Decrypt is the same stuff, but in the other, using decrypt mode instead of encrypt mode, which decrypt mode and encrypt mode, I would assume are integers. Yeah, just integers, they're just flags. Because, I don't know, I don't miss Java. I haven't been using it much, and I don't miss it. But anyway, we're encrypting the same exact string twice with the same exact key. And our crypto texts, of course, are not on the screen, so I can't point to them dramatically. Our crypto texts are very different. That's because we're using that padding algorithm. So even if we send 1 bit, even if I had 1 bit of entropy in my message, just a yes or no answer, 1 bit, the crypto text is going to be significantly different because we're adding different padding each time. We're taking that information, that meet us at the stick string, adding a whole bunch of random garbage to the end of it, encrypting that, and then during decryption, we just throw away all the random garbage. But now we eliminate those brute force attacks because you have to guess all that random garbage, and we prevent another attack where you see all the messages, all the encrypted messages, and you say, oh, they sent the same message. I see the same crypto text multiple times, therefore it's the same message. That attack doesn't exist either. They don't gain any information. By looking at this, they don't know I just sent meet us at the stick twice. They don't learn anything from looking at this ciphertext. They can't get any information out of this, which is the way we like it. We like that. All right. So that's my quick demo. And let's go to HTTPS. We got a whole bunch of good encryption stuff to talk about. If this spills over to Monday, that's not the worst thing. Nothing new there. All right, let's talk about HTTP over TLS or SSL. So HTTPS most accurately is HTTP over TLS. That's if I'm being verbose or I'm being accurate, that's what I'm going to call it. When I expand it, some people call it HTTP secure, just reading out the letters, or secure HTTP because it sounds better. Whatever you call it, we mean HTTPS. Those are all the ways you can expand this acronym. When we use HTTPS, one of the best features of this, and we'll see why in a second, is that we as developers, as web app developers, we don't care that HTTPS even exists or that it's a thing. All the code that we write, we just code to HTTP, and that HTTP code works exactly the same even though we're using HTTPS. So it's not another protocol. It doesn't replace HTTP. It's adding another layer on HTTP, which is somewhat invisible to us, and it is invisible to us when we're writing our actual apps and adding features and worrying about user experience and all that stuff. We don't care about any of that. So the difference is that after we send a message over the TCP stream, or when we receive a message over the TCP stream, it's encrypted as it's being transported over the internet. So we say this is using TLS. So we say that this is HTTP over TLS because when we get our HTTP response and we say, hey, send this to the user, it's encrypted and then sent over the TCP socket. When we read off of the TCP socket, it's encrypted, it gets decrypted, and then we read it. So we're still just working in bytes off the TCP socket. So everything we wrote all semester and all the homeworks, all that code is 100% reused when we move to HTTPS. We don't have to change anything in there. We're just going to add a layer of encryption. I say SSL/TLS. So the library or the protocol used to be Secure Socket Layer, SSL. When SSL got to version 3.0, they said, let's rename this TLS and call it Transport Layer Security. I'm sure there's a perfectly good reason why they changed the name. I don't know, because honestly, I don't really care that much. But now it's called TLS, just to be confusing. I think that's the actual reason. They just want to confuse us. So there's two different names for the same thing. So some of the libraries, including the library we'll use way at the end of this, this lecture, OpenSSL. It's named OpenSSL, but it actually does TLS these days. Nobody uses SSL anymore. So TLS is just the newer versions of SSL. But they didn't go through and rename like all the libraries and everything around this protocol. So you'll still see SSL pop up from time to time. But rest assured, it's going to be TLS now because SSL will get rejected by every browser. They're not going to speak SSL. So it's TLS, but if you see SSL, it's the same thing. In terminology only. So on our protocol stack, we used to have the IP headers, then the TCP headers, then the HTTP headers. TLS is just going to go right in between HTTP and TCP. So our TCP socket, the way we do this in the code is add this layer right in front of our TCP socket. So over TCP, everything's encrypted. But TCP doesn't care that it's sending encrypted messages, just like it never cared that it was sending HTTP or WebSockets. It just doesn't care. All TCP cares about is that it's sending a bunch of bytes over the internet. Actually, it doesn't even care that it's talking to the internet. The IP cares about that. TCP doesn't care. So TCP is now transporting encrypted bytes, but to TCP, it's the same thing. Once we get those bytes to our system, but before it gets to our application, or sometimes in the application, depending on how it's configured and everything. Oh, my arrow. It's encrypted. So TLS will encrypt or decrypt, depending on which direction we're going. But it just sits in front of the TCP socket. So those encrypted bytes coming through TCP, goes through TLS, gets decrypted, and then goes to our app. So our app still just speaks unencrypted HTTP and doesn't need to care that those bytes were encrypted. Very nice feature. Get to reuse everything. We don't have to think about TLS very much. Until we go to add encryption, we do have to add the encryption part at some point, but our code, like we can have an entire repo for our app that only speaks HTTP, and it's perfectly fine. Well, we can talk about that next week, but yeah, I can't. It would be too much of a tangent. I got all next week to talk about that. But we'll use a reverse proxy. The reverse proxy will decrypt and then send an unencrypted message to our machine. But that's internal to our server where people can't eavesdrop on it. So we're going to get away with that one. So we don't have to speak HTTPS at all, except at the reverse proxy level, which is next week. So we just use HTTP. That's it. No changes to our server whatsoever. Just a change in the way that we deploy our server. So how do we use TLS? That's what TLS is. It's just a layer in between HTTP and TCP. But how do we use this? We have one big problem, which actually came up on Wednesday's lecture. We have this big problem. We want two-way encrypted traffic. Server sends encrypted traffic to us. We send encrypted traffic to the server. I guess in this class, we are the server. So we send encrypted traffic to the client. The client sends encrypted traffic back to us. The problem is all we have is a public-private key pair that the server has that's verified by a CA. We didn't get to the CA content last time. I actually put it towards the end of this lecture. So we'll talk exactly about what a CA does. But a CA verifies your public key, is the TLDR of it. So we have a server with a public-private key pair, which means that the client can send encrypted traffic to the server. And that's it. Like, that's all we have. That's not quite enough to get where we're going. So we need some extra, we need something extra here. Now, we could generate a public-private key pair at the client, have the client send a public key to the server. That's not actually how we do it. That has some issues, and we're not going to do it that way, not the least of which is performance. Public key encryption, as it turns out, is really slow. It's an exponent, modular exponent. That's not too bad, I guess. But if you have a really long message, you have to do that many, many times. And, it's just slow. So we're not going to do it that way. What we are going to do is another handshake. So we're going to do a handshake that's going to agree on what we call a symmetric encryption key. So we're not going to use RSA. We're not going to use any public key encryption for our actual communication. We're going to agree through a handshake on a symmetric key, and then we're going to use that key for encryption. With symmetric key encryption, as opposed to public key encryption, there's only one key. There's no public and private key. We're going to agree on one key, and then that key is going to be used by server and client to encrypt and decrypt. So what we want is that symmetric key, a way to securely agree on that symmetric key, and then use that symmetric key for all of our communication. So how do we communicate this with keeping in mind that anyone can be eavesdropping on this communication? So we want encryption, so even if somebody's in Wi-Fi range and reading our packets, we want encryption so even somebody doing that can't eavesdrop on our communication. But this handshake cannot be encrypted because this handshake is where we're actually agreeing on how we're going to encrypt. So that none of this can be encrypted, which can cause some problems. So we got to think our way through that. So through this entire process, how do we make sure that somebody who knows everything that's communicated between client and server, they still can't figure out what's going on? That's what we want. That's our goal. So there are a lot of different ways to do this. I'm just going to show you one way, the Diffie-Hellman Key Exchange. There are other ways. There are lots of protocols, lots of algorithms to be able to do this. I'll show you one just as a proof of concept that says, hey, look, we can do this. We have the technology, we have the math to be able to handle this. So Diffie-Hellman Key Exchange. Are you glad I don't have exams in this class, by the way? I'd be like, explain to me what Diffie-Hellman Key Exchange is. Talk to me about RSA. So Diffie-Hellman Key Exchange, since it's only homework in the project, you don't, you know what I'm saying. So with Diffie-Hellman Key Exchange, the server and the client, I'm thinking about I should have exams. The client and the server are going to agree on two values, a prime number P that generates a group G. Now, if you haven't taken high-level discrete math, algebra, if you haven't taken like advanced algebra classes, which I'm sure probably 0 to 1 of you have, to have a prime number generate, it's like a 300-level math class. Like I'm sure most of you haven't. But for a prime number to generate a group G, we're going to say that for every value from 0 or from 1 to p minus 1, G to the I mod P is a unique value, which means I can take P and continuously multiply it by itself. And each time I multiply it, I'm going to get a unique value that's going to give me every value up to G. That's a typo. Wait, did I write this backwards? Apparently I have to go back to math. We say G generates the group. No, P generates the group. With the group no, I do have it right. G generates the group P. I said it backwards in the first one. Yeah, I have to go back to that class. It's advanced math for a reason. It's tricky. So G generates P. So G multiplied by itself is going to give us all of the values from 1 to P. So if we keep multiplying G by itself, it generates the group. So if we take two values in this group and multiply them, we're more likely to get another unique value in the group. If we didn't have this case, then when we keep multiplying G by itself or G to any power, we wouldn't be able to, I like to think of it as fill up the group P, all the values from 1 to p minus 1. We wouldn't be able to fill up that group. We would be, like say we skipped every other one, and we didn't get every value in there. We wouldn't have a group of size P, which means we wouldn't have P number of values that we can use, which really limits the domain that we're working with. We want to fill up P. We want to use everything in P. Every value 1 to p minus 1 should be a valid thing. And we're going to compute everything by taking G to a power mod P. So we want to be able to have every value available to us. For example, if G equals P, we would only have one value, and that wouldn't really do us any good. So we want to make sure G generates P. These values are both public, P and G. So now that we have P and G, the client and server are both going to think up some random number. It's completely random, different for every communication, completely random numbers, maybe not possibly completely depending on implementations, but at the very least to us, completely random values. The client's number we're going to call A, and the server's number we're going to call B, and these are private. These must be private for the key exchange to work, or else the key exchange is basically a public key exchange for anybody eavesdropping. These are private to the extent that the server can't even know the client's value A, and the client can't even know the server's value B. They're that private. Only client knows A, only server knows B. The client's going to compute G to the A mod P and send that to the server. The server is going to compute G to the B mod P and send that to the client. So they're each sending their value, G raised to their value mod P. Since G generates P, we should get the full force of P minus 1 different values in this range, in the domain. Range, I guess, is the technically the right term there. I haven't used those terms in a while. But anyway, we're going to send those to each other, and then client and server are going to take that value that they get and raise it to their own power. So each, at the end of this process, is going to have G to the AB mod P. So we have a shared secret where neither of them know what the other's secret value was, but they both have a shared secret value that's G to the AB mod P. And the only thing that was communicated was G to the A mod P and G to the B mod P. Those are the only two things that were communicated across the network. And we know from last time that discrete log is a cryptographic primitive, which we believe is very hard to compute. So we can't take these values and take the log-based G mod P and compute A and B. We can't do that because discrete log is really hard to do. At least we hope. So since that's hard to do, client and server can't compute A or B, the other one, and the eavesdroppers don't know how to decode this. And the eavesdroppers can't take, so they'll have both of these values. Any eavesdropper has both of these values, but you can't take those two values and compute G to the AB mod P, because you can't take the discrete log and compute B and then raise the other one to that power. They just can't do that mathematically. We believe that that's too hard to do, and we're going to bank our encryption, our entire encrypted lives on it. This secret is going to be used to either generate the symmetric key or thrown into a function which, thrown in a function which generates the symmetric encryption key, or just uses as the symmetric key directly. Usually you're going to want to throw in a function that generates the symmetric key because you want some certain properties out of your key, a certain length or whatever your algorithm calls for. You're going to want to do that. Like, I don't have a good example, but that's going to be used to generate your symmetric key. So now we have a shared symmetric key, which any eavesdropper can't know. They can't know that unless they break discrete log. Can anyone understand what Jesse is talking? No. I mean, I'd be happy to explain it more in depth, but I would need a specific question other than what? Yeah, I like the paint example. I should steal that in my slides. If you mix the paints together, you can't unmix a paint, is effectively what we're doing with the math. G to the A mod P, or it's G to the A quantity mod P. So it's always, like I put the braces here, but those braces could be here as well, or parentheses, the more mathematical way of putting it. Parentheses. I do braces because that's the LaTeX notation for it. so I was just used to that. But yeah, it's G to the A quantity mod P. So you do the exponentiation first and then mod P. Exponentiation first, I guess I should have extra parentheses here to make it very clear. G to the AB quantity mod P. All the exponentiation is first and then the modulo. Mathematically speaking. In implementations, there's all kinds of optimizations that, it doesn't matter. That they don't actually compute the exponentiation and then mod P it. They'll optimize the crap out of it with really fancy algorithms. The image is not, Trevor, I don't think is in the room, but the image is for Diffie-Hellman. Does cross-site request forgery token require max age? I don't think I put it in the homework doc, so therefore it doesn't. Probably should have a max age, but it's not set in a cookie, so it wouldn't have a max age in a cookie. But no, you don't have to have them expire since it's not in the doc. Yeah, I know, Nicholas. He just likes talking during lecture. It's fine. All right, so we have a shared secret key, and we're going to use that for symmetric encryption. I won't talk about symmetric encryption algorithms aside from just a brief explanation on this slide. One of the most common ones is AES, which replaced DES, which is broken now because people figured out how to break it. But AES is still standing fairly strong. The very brief one bullet point description is it scrambles up the bytes and uses a whole bunch of XORs. So it takes the key and then generates really long, just random strings from that key, and then XORs the message like a whole bunch of times and just really scrambles up things with XOR operations. So then if you do the same exact operation again, it undoes all the XORs, much like the masking in WebSockets. It'll undo all that stuff. So it's really scrambled, really messed up to anybody without the key. But if you have the key, you can undo all of the XORs. It's just a whole bunch of XOR operations. So that's the short story of how AES works. It does not rely on any cryptographic primitive. It's just a whole bunch of XORs. So it could be broken without breaking all of encryption. And there are theoretical attacks. Some of them have got a lot of publicity. There are some theoretical attacks for AES where you could either decrypt or generate encrypted. I'm thinking of SHA with that one. SHA, they generated hash collisions. But there are theoretical attacks to break AES, but no practical attacks yet. So there are some really mathematically complex research out there, some papers that were published and got a lot of traction that said AES is broken, everybody watch out. But they're only theoretical at the moment, so we're still using it out there. Until somebody comes up with a practical attack that actually works, we're going to keep using it. And to actually do all this, we have the actual handshake. So I explained DES, but there's more to the handshake itselth. So SHA-1 has been shattered. Yeah, SHA-1, I think that's where they could generate the PDFs with hash collisions. Yeah, that's what I was trying to think of. But then we use SHA-256, and that one's still seeming to be pretty good. Eventually, we'll all move to SHA-3, which is out now. So for the handshake, the client says, hello, hello, server. Here are all the algorithms that I support. Server says, okay, I see what you support, and these are the ones that I choose for this connection. The server sends its certificate, usually along with the hello. They'll generate their parts of the symmetric key, their partial keys, send them to each other. The server is going to sign its portion of that private key, that private symmetric key. It's partial symmetric key. It's part of the partial symmetric key. It's going to sign that with its private key from its certificate. Signs it with its certificate. Says, here's my part of the symmetric key, right? Sends that off. Once we have the partial keys, client and server compute the rest of it, and then they have the symmetric key, and that's what they're going to use to encrypt all traffic after this handshake. So we did all this. I don't want to talk about all that yet. So we did all of this public key encryption. We talked about RSA. We're going to talk about certificate authorities. We did all of that so the server can sign its partial symmetric encryption key. That public-private key pair wasn't actually and isn't actually ever used for encryption. We have this whole system of certificate authorities out there, all this stuff to handle these public keys to sign one thing. That's it. Like, that's all we really use it for in encryption, at least in HTTPS. That's all we use it for, is to sign one thing. End of story. That's it. Never actually used for encryption. So don't fall into, oh, we have public certificates, that's how we use encryption. You just use their public key, and that's how you encrypt stuff to them. You never actually use that public key from the cert to encrypt anything that you send to the server. You just don't do it. It's all symmetric key encryption, which, as I mentioned, public key encryption is pretty slow. Symmetric key encryption, pretty fast. It's just a bunch of XORs. XORs are extremely fast. They're bit-level operations, which means our CPUs have that operation as a fundamental operation. I keep saying operation, but there's a, the CPU can just compute that directly. We don't have to have an algorithm that's going to make multiple calls to the CPU, multiple calls to the processor. It's right in that instruction set. Hey, XOR these two things. Gotcha. It's circuits at that point. It's fast as light. It's not literally, but it's as fast as electricity. It's extremely fast. So this gives us a really nice, so why use this symmetric key? One, speed, and two, it gives us something called forward secrecy. And this is a really powerful concept. So with forward secrecy, we're using this one-time encryption key, this one-time symmetric key. If you connect to the same server again, you're generating a new value A, server's generating a new value B. You're getting a different encryption key every single time you connect to the same server. You're not reusing a symmetric key. So now, say later on down the road, somebody's able to crack that certificate or hack the server, get their private encryption key that's associated with that certificate. Seems pretty bad, but what can they actually do with that? So say they were eavesdropping earlier, they got all this encrypted traffic, they eavesdrop on your key exchange, and they get all of the encrypted traffic after that. And then they steal your private key later. Well, they can verify the signature, but they could already do that, the signature of the partial key. They could already do that because there was no encryption there. So they don't gain any information, and they can't gain any information about that private key. They still have to break discrete log. Those values were already in the clear. They already had that information. So they don't gain anything by stealing your private key from your server. The only thing they could do is sign things, sign that key exchange part. They could start doing that, but it's only an active attack. They can't go backwards and take everything that they stored, all that communication they stored, and decrypt it. They can't do that. That's what we call forward secrecy. They have to be actively attacking you to be able to get any information. So forward secrecy, even if they're storing all our communications, well, that was a one-time key that they can't compute because it can't break discrete log, and server and client never stored A and B. You throw those away once you compute the symmetric key. There's nothing they can learn. Forward secrecy, very beautiful, very powerful thing. And I mentioned quite a few algorithms here, RSA, Diffie-Hellman, AES, SHA-256, I guess. These are not the only algorithms used. There are all kinds of algorithms that are used. And during that key exchange, the first thing was, these are the algorithms I support. OK, these are the algorithms we're going to use. TLS itself is designed to be very abstract. You can think of it as just an interface. It's just a protocol that says how are we going to agree on the algorithms to be used. And TLS can be used for algorithms that we haven't even come up with yet, that don't even exist yet. TLS is made to be future-proof, or at least the current version of TLS. There were obviously versions that weren't future-proof through the days of SSL. TLS 1.0 isn't used anymore, but 1.1, 1.2, 1.3, they're made to be pretty, I guess that's contradictory. They're made to be future-proof, but there's all kinds of versions of it, so I guess they're not doing too good of a job. But they're not hard-coded to any algorithms. So these algorithms can be swapped out. During the handshake, you say, I support RSA and Diffie-Hellman and AES, or you say, I support elliptic curve encryption and these other algorithms, elliptic curve key exchanges and things like that. So it's very flexible to be able to do that. And if we're keeping track at this point, I think this is as good a point of any to say this. If we're keeping track, when you connect to a server, there's quite a bit of back and forth that has to happen before you can send any information to each other. So you have first the TCP three-way handshake. You send, I'm going to blank on it, a SYN, an ACK, and a SYN. And then you have to have the key exchange. These are the algorithms I support. These are the algorithms we're going to use. Here's my partial encryption key. Here's my partial encryption key. And then you can finally say, here's my first HTTP request. Can you give me your home page? There's quite a bit of back and forth just to be able to get any communication working between a client and a server. There are new protocols like HTTP2 and QUIC. I think QUIC is HTTP2. But there are new protocols coming out that try to combine all that and say, look, we're just going to encrypt everything. Let's put that right in our initial handshake to be able to get that down. But we have like 3 round trips, I believe it is, just to be able to get any communication in there. So when you have your delay for that first connection of how to connect to a website, or this is I used to demo this in 199 actually, but go to your browser and see how long it takes to get one back and forth for the root homepage of a server, and then go to your console and ping that same exact server, and you'll see how much less time the ping takes than it does to get the homepage. And part of that, part of that is there's a lot more information being sent when you're getting the homepage, but that doesn't really account for very much of it. What accounts for it is those 3 round trips, just to be able to establish a connection, establish an encrypted connection between the server. So take your ping time, at least multiply it by 3, and then that's where you're starting. That's your minimum, absolute minimum if you're sending 1 bit of information that you can get. A lot of that's just because there's so many round trips to establish a connection. Another reason why WebSockets are so much more efficient, you're just reusing the same connection, and you can encrypt that. You can use, we use the WS protocol. You can use WSS, which is WebSockets over TLS. Encrypt that connection. You have your symmetric key already agreed upon, and then it's just sending information back and forth without reestablishing a TCP connection. I want to make sure I got that in there. We got that in there. There's one big downfall to this. TLS is in between TCP and HTTP. So guess what's not encrypted? It's all your TCP IP headers. Your TCP IP headers are not encrypted. We can't encrypt those. Well, at the very least, we cannot encrypt the IP headers ever. Because how are the routers of the internet going to know where to send this information if you encrypt it? They need to read, most importantly, the source and destination IP addresses, or at the very least, the destination IP address. There's nothing we can do there. That IP address has to be out in the open because the routers need that information. They need to know that. And then whoever we're connecting to, we would like source IP address too, so they can send us information back. Like, that's a useful thing to have. So those things have to be in the open. I suppose that could be encrypted some way, and they can decrypt. But the way things work, TCP IP headers, not encrypted. And this is why this is why VPNs are still popular. We still use VPNs, even though pretty much everything is HTTPS out there these days. We still use VPNs because they can still see who we're talking to. They can't decrypt our actual HTTP messages or our WebSockets or any of that. They can't decrypt any of that to see what we're saying, but they can still see who we're talking to. And they can see like how many bytes we're sending. They can start piecing things together and start learning something about what we're doing. That can't be encrypted. So if you use a VPN, you're effectively bouncing your traffic off another server, and then anybody eavesdropping can either see the source IP address or the destination IP address if they're on the other side of your VPN, but they can't see both. So if I do that thing where I get crazy and put my box up here that's sniffing all the packets and you're using a VPN, I'll still see that you're using a VPN. I just won't know what you're doing on the other side of that VPN, what your ultimate destination of your packets are. So for what it's worth, if you're going to use things like encryption, VPN, at least know what it's protecting you from and what extent it's protecting you. Like your ISP knows you're using a VPN because they're going to look at the IP and be like, oh, that's the IP address of a VPN. My brain there. Of a VPN. They're connected to a VPN. And they're probably going to assume you're up to no good, but they can't know exactly what you're doing. They know you're up to something that you want to hide. Yeah, or create your own VPN, exactly. Yeah, you'll host your own VPN, and then you can get extra security. You can say, oh, they're connecting to that server over there, and I don't know anything about that. It looks like a private server. They don't really get to know that it's a VPN. All right, we have a big vulnerability here. Any questions at this point, by the way? I haven't been stopping for questions very much. My second favorite anime? I'd probably say Dragon Ball Z. I tend to not even think of that as an anime. It's so mainstream, but Dragon Ball Z. Like I don't know, like is Sailor Moon an anime? I don't know. The answer is yes. Is Pokemon an anime? That's like the most borderline in my opinion. Technically, yeah, I guess, but I don't know. But I'll stick with Dragon Ball Z. The real questions. Yeah, I don't know about third favorite. Maybe Pokemon. I haven't really watched much Pokemon though. All right, so we have a big vulnerability here. When we're talking about public key encryption, when we need to get that public key out to everybody. So what happens during the handshake is the client says, yo, give me your public key. And the server says, here's my public key. There's an attack here called the man-in-the-middle attack, because only men perform this attack, apparently. I don't know. Maybe that's something the next thing to be changed in name. But for now, it's the man-in-the-middle attack, where somebody's eavesdropping on that communication in a way where they can intercept the packets. So not just sniffing the packets out of the air, but like controlling a router and being able to intercept that packet, not send it to the server, and then respond with their own packet. So they're actually in the middle of the communication and blocking communication with the server. So you send, hey, give me your public key. The man in the middle says, okay, let me respond with my public key, send that to the client. And then when the client says, oh, cool, now we do the key exchange, we do all that stuff, you're actually talking to an attacker and not the server. And now that you have the public key of the attacker, you're going to use that for verification to verify that that partial key is signed. And then encrypt using an encryption key that only the attacker knows. And then you're just communicating with an attacker and you have no idea. They're just masquerading as the server that you're communicating with. This is bad, obviously. And it's if you control a router or something, you're at a point where you can intercept that traffic, Or you masquerade as a router. You set up your access point and name it UB Secure or EDU Roam. It happens. No password and automatically connects. It happens. Then you can have this attack and not know that you're communicating with an attacker. This is bad, and certificate authorities are here to fix this problem. So we don't just hand out public keys. Our servers don't just hand out public keys. First, our servers, we have to get those public keys signed by a certificate authority. So a certificate authority is a trusted source, a trusted entity that has a known public key that everybody knows and agrees upon. And these are called root CAs. These are installed with either your operating system or your browser. So at some level, this is where at some level we have to assume something's secure. We assume that when you install your operating system and get these root CA public keys, we assume that that's safe and secure. You can go verify those keys and add some extra security if you'd like. But we're going to assume that we have the correct root CA keys. And then whenever we get a certificate, sorry, I haven't introduced certificate yet. Now whenever we want a public key, we're not just going to get the public key. The server is going to take that public key, go to the root CA or just a CA, which I'll talk about in a second, have that root CA sign that public key with their private key, and then that's what we call a certificate. And then instead of just sending their public key, you're going to send this certificate to your clients. The client's going to say, give me your public key. You say, here's my certificate. The client can verify the signature of that certificate, and that signature, it should be signed, cryptographically signed with the private key of the CA. We're going to take our public key for that CA, verify the signature, and then that'll say, I'm this CA. I verify that this is the public key for this domain name. So they signed that key for that domain name to verify that this came from the owner of that domain, and the CA is going to verify that you control that domain name. And we use cryptography and hashing. I like certs because we get to use both of those. So they sign it with their private key and also hash the entire certificate and signature so you can verify that nothing was tampered with. Now, the man in the middle, if they don't have that root CA's private key, they can't fake these certificates. Just can't happen. So we usually don't go to root CAs. Root CAs are the only things that are trusted, but we go to certificate authorities, just regular non-root CAs. So this is what brings up something called a keychain. So we're going to get our public keys signed by a certificate authority using their private key. They're going to sign with their private key. Their public key is a certificate that's signed by possibly another certificate authority. And then we keep going up this chain until we have a certificate that's signed by a root CA. So we'll have some chain, and as long as that chain ends with a root certificate authority, then we can verify the CA, we can verify the next CA, verify the next CA, then verify the server eventually. So we have this chain. So if you look at any certificates, you'll see the whole chain, which is usually, every one I see is two CAs. There's a CA, the server, the CA, and then the root CA. It's a pretty flat structure, but it could be a very long chain. As long as it ends in a root CA, we're going to trust that thing. If it doesn't end in a root CA, we're going to call it a self-signed certificate, and we're not going to trust it. Which, I don't know if we can really do the lecture question. I didn't really get to what we can do with the question. Let's do another free question. I'll save that one for Monday. What letter do we want today? What? An emoji. How about C? So the answer is C to the lecture question because I didn't get far enough to do the one that I have prepped. C is the answer to the lecture question. C.